Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous couple of lectures we were discussing about Green-Ampt equation for infiltration and infiltration equation, that is corresponding to potential infiltration rate and also cumulative infiltration we have derived by combining continuity and momentum equations for getting the expressions corresponding to Green-Ampt equation. After that we have derived the equation corresponding to ponding time, and by making use of that principles we have found out the expression for quantifying the infiltration after ponding. So, today what we are going to do, we will work out some of the numerical examples related to Green-Ampt equation for making the concepts clearer. First example is, assume water is ponded to a small depth on the surface, compute the infiltration rate F and cumulative infiltration rate capital F after 1 hour of infiltration into a loam soil that initially had an effective saturation of 25%. Ponding depth can be neglected. Use theta E is equal to 0.434, psi is equal to 8.89 centimeter, K is equal to 0.34 centimeters per hour. So, what we need to determine? We need to determine the infiltration rate F and cumulative infiltration capital F. Certain data given to us, by making use of that we need to calculate the infiltration rate and cumulative infiltration. First let us see what are the data provided to us. Data given are effective saturation SC is 25%. SC is given, that is effective saturation is 25% given, we were using the notation of SC. Then theta E, what is it? Theta E is effective porosity, that is 0.434. Then psi is the soil suction, negative pressure, psi is given as 8.89 centimeters and hydraulic conductivity K is equal to 0.34 centimeters per hour. Now, we need to compute the infiltration rate F after 1 hour of infiltration and cumulative infiltration rate capital F after 1 hour of infiltration. We are assuming a uniform intensity of rainfall for 1 hour. We need to calculate the cumulative infiltration and infiltration rate corresponding to that particular time. So, definitely from these data it is very clear that we can make use of Green-Ampt equation. We can start solving the example. Green-Ampt equation is given by this equation, f of t is equal to kt plus psi delta theta ln 1 plus f of t divided by psi delta theta. And here we are having k is given to us, psi is given to us, then what else? Delta theta is present. Delta theta we need to calculate. For that we have already found out an expression, that is delta theta is equal to 1 minus SC theta E. Based on the effective saturation and effective porosity, we have derived the equation for soil moisture deficit delta theta. So, SC is known to us, theta E is known to us. If SC is 25% and theta E is 0.434. So, delta theta can be calculated as 0.326. Just substituting in this equation and calculating that. After that we will substitute all the given values in our Green-Ampt equation. So, psi delta theta component is there, that we can calculate. Psi is given as 8.89 centimeters and delta theta we have already calculated as 0.326. Psi delta theta will be coming out to be 2.898 centimeters. After substituting these values, we will get f of t is equal to k is 0.34. So, f of t is equal to 0.34 t plus 2.898 ln 1 plus f of t divided by 2.898. Look at the equation carefully. You can see capital F of t, that is the cumulative infiltration corresponding to time t. F of t is present on both the sides of equation. It is a nonlinear implicit equation. So, we cannot directly calculate the value. So, we may have to go for some trial and error method to get the correct F of t, cumulative infiltration value, by making use of this particular equation. So, F of t, I have repeated the equation from the previous slide over here, and we have been given at time t is equal to 1 hour, we need to calculate all these things. So, we can substitute t is equal to 1 hour. So, F of t is equal to 0.34 plus 2.898 ln 1 plus f of t divided by 2.898. So, here what we will do, we will make an assumption for f of t initially. We are going to solve this particular equation by the method of successive substitution for the calculation of infiltration at t is equal to 1 hour. So, first assumption, there should be a first assumption for the value of f of t. By substituting that value on the right hand side, we will calculate the f of t on the left hand side. If both of them are matching, our assumption is correct. If it is not matching each other, if it is not equal to each other, we have to again reassume the value corresponding to f of t on the right hand side until we reach the equal values, until we obtain the same values on left hand side f of t and the value which is assumed for f of t on the right hand side. So, in what way we will assume the first value? So, the assumption is made in such a way that the trial value of f of t is taken as kt, that is k is 0.34 and t is 1 hour. So, it can be calculated to be 0.34 centimeters. So, first assumption corresponding to capital F of t is, we are assuming the cumulative or the potential infiltration value, cumulative infiltration value is 0.34 centimeters. Then we will substitute in here on the right hand side and we can calculate f of t on the left hand side. After that, this calculated f of t can be represented by f dash t. This f of t versus f dash t versus f of t. F dash t is the calculated value and f of t is the assumed value, whether these two are in proper match. If it is not there, same procedure will be repeated with new assumptions. So, cumulative infiltration at 1 hour with the assumption of f of t is equal to 0.34 can be calculated by substituting in that equation. So, here we have substituted f of t is equal to 0.34. This can be calculated as 0.66 centimeters. So, we got the cumulative infiltration f of t equal to 0.66 centimeter, but our assumption is 0.34 centimeter. So much of difference is there, 0.34 centimeters and 0.66 centimeters. So, this process has to be repeated until we get both the values same. So, next assumption what we will do, we will substitute f of t as 0.66. The value which is calculated over here based on the first assumption, that will be substituted for capital F of t on the right hand side. Again f dash t will be calculated and again the check will be done until we get the matching values. Provided the values over here and initial guess was 0.34, corresponding to that we got f dash on the left hand side to be 0.66. Then the value 0.66 is assumed, taken as the assumption, and that is substituted on the right hand side. We got 0.944 f dash. That is again substituted on the right hand side and we got the value corresponding to f of t on the left hand side, that is f dash as 1.15. This procedure is continued until we get the same values, that is our assumption and the f dash calculated based on that assumption match each other. So, finally, we got a match keeping the value as 1.64 centimeters. Substituting f is equal to 0.66 centimeter, it gave f is equal to 0.94 centimeter. And then the process is repeated. After several iteration, f converges to 1.64 centimeter, that we have seen the final value coming, it is not changing. Even after 1.64 is substituted in the Green-Ampt equation on the right hand side, f dash calculated was 1.64. So, this is our final cumulative infiltration 1.64. So, capital F of t corresponding to 1 hour is calculated as 1.64 centimeters. Now, what we need to compute? We need to compute the infiltration rate. So, infiltration rate at 1 hour we need to calculate. So, same Green-Ampt equation corresponding to infiltration rate will be utilized, that is small f is equal to k psi delta theta divided by f plus 1. So, psi delta theta is known to as capital F, that is the cumulative infiltration which we have computed in the previous slide. And hydraulic conductivity is already given to us, we will just substitute in this equation and we can calculate the infiltration rate as 0.94 centimeters per hour. Cumulative infiltration we have calculated as 1.64 centimeter, that is substituted over here in the infiltration rate equation to get the infiltration rate. So, Green-Ampt equation, both the equations corresponding to infiltration rate and also cumulative infiltration we have made use. By making use of the cumulative infiltration equation, capital F of t were present on both the sides of the equation. So, we were doing a successive substitution by making a proper assumption for capital F of t. And we have continued the process until we get a proper match between the assumed capital F of t and the calculated F of t value. So, we can solve one more example. For a soil of 30% initial effective saturation, calculate the ponding time and the depth of water infiltrated at ponding subject to rainfall intensity of 2.5 centimeters per hour. Theta E is given to us 0.486, psi is 16.68 centimeter and hydraulic conductivity K is equal to 0.65 centimeters per hour. So, the data which are given to us are effective saturation SE, effective porosity theta E, psi is 16.68 centimeters, K is equal to 0.65 centimeters per hour. Rainfall intensity is also given to us, that is I is equal to 2.5 centimeters per hour. We need to calculate the ponding time Tp and the cumulative infiltration at ponding. Ponding time Tp and the depth of water infiltrated at ponding. Depth of water infiltrated at ponding is representing the cumulative infiltration corresponding to that particular time. So, first we need to calculate the ponding time. After that, we need to calculate the cumulative infiltration by making use of the rainfall intensity given to us. We are having the expression for ponding time Tp, that is given by k psi delta theta divided by I into I minus k. K is given to us, psi is given to us, delta theta can be calculated, that is the soil moisture deficit can be calculated, and intensity of rainfall is also given to us. So, we need to calculate delta theta as we have done in the previous example. We will be calculating delta theta by making use of effective saturation given, that is SC is equal to 30% and effective porosity theta E is equal to 0.486. What is the expression for delta theta? Delta theta is given by 1 minus SC multiplied by theta E. Just substitution. It can be calculated as 0.34. Delta theta is calculated as 0.34. So, now we can come back to the expression Tp. Okay, Tp is containing psi delta theta. So, psi is given as 16.68, psi k is given as 0.65 centimeters per hour, intensity of rainfall I 2.5 centimeters per hour. So, just substitution in the expression Tp, all the given values and calculated value corresponding to delta theta we have substituted, and we can calculate Tp as 0.8 hours. Ponding time is found out to be 0.8 hours. Now, what is the thing which is asked in the question? We need to find the depth of infiltrated water at ponding or the cumulative infiltration Fp. F of P, cumulative infiltration, intensity of rainfall is there, I is given to us, and time of ponding is also available to us. So, by multiplying those two, we can understand or we can calculate how much is the quantity of water infiltrated into the ground during that particular time of Tp. So, the expression we have already seen, f of P is equal to I Tp. We are substituting for I and Tp, which is calculated. I is already given to us, it is coming out to be 2 centimeter. 2 centimeters of water is infiltrated into the ground. That is the quantity of water which is infiltrated, which is termed as the cumulative infiltration just before ponding. Now, we will move on to third example, in which we will calculate the infiltrated water or the quantity of water which is infiltrated after ponding. Let me read out the question. Rainfall intensity of 4.5 centimeters per hour occurs for 1 hour over a soil with an initial effective saturation of 30%, given that theta E is equal to 0.423, psi is equal to 29.22 centimeters, k is equal to 0.05 centimeters per hour. Compute the ponding time, the depth of water infiltrated at ponding and infiltration rate, and C is the cumulative infiltration and the infiltration rate at 1 hour of rainfall after ponding. So, we need to calculate 3 components, that is, first one is ponding time, second one is depth of water infiltrated at ponding and infiltration rate, and third part is cumulative infiltration and infiltration rate after 1 hour of rainfall. So, we need to check this 1 hour, within 1 hour whether the ponding is occurring or not. If the ponding time is calculated to be more than 1 hour, then we can assume the intensity of rainfall as the infiltration rate, and we can calculate easily how much is the cumulative infiltration. So, first we need to check what is the ponding time. So, let us see what are the data given. Effective saturation C is equal to 30%, effective porosity theta E is equal to 0.423, psi is equal to 29.22 centimeters, k is equal to 0.05 centimeters per hour, rainfall intensity I is equal to 4.5 centimeters per hour for 1 hour. So, 1 hour we can assume uniform rainfall intensity. Now, let us see what are the things to be calculated. We need to compute, first one is ponding time Tp, we are having the expression for that. Second, the depth of water infiltrated at ponding, capital F of P, and the corresponding infiltration rate, that is the potential infiltration rate small f of P. Third part is cumulative infiltration and the infiltration rate after 1 hour of rainfall. After 1 hour of rainfall. So, this we will get a clear idea when we determine the value corresponding to ponding time. If ponding time is less than 1 hour, we need to calculate the infiltration between the ponding time and the time given, that is 1 hour. Otherwise, if it is less than that, we can just multiply the rainfall intensity with the time given to us. Let us calculate first, that is the ponding time Tp. We are having the expression for Tp, k psi delta theta divided by I multiplied by I minus k. So, the values are given to us, psi is equal to 29.22 centimeters, hydraulic conductivity k is equal to 0.05 centimeters per hour, Now we are having delta theta. As we have done in the previous examples, we need to calculate the value corresponding to delta theta. Effective saturation and effective porosity are given to us. So, we will be substituting in the expression for soil moisture deficit. Delta theta can be calculated as 0.296. Now, we can substitute psi, k and delta theta in the equation for ponding time and also intensity of rainfall. So, Tp is 0.05 into 29.22 into 0.296 divided by 4.5 multiplied by 4.5 minus 0.05. Rainfall intensity is substituted as 4.5, which is given to us. So, Tp can be calculated as 0.02 hours. So, now we have calculated the value corresponding to ponding time by making use of the equation for Tp, and it is found that it is only 0.02 hours. Within 0.02 hours, water starts ponding on the ground surface. Second part is depth of water infiltrated at ponding. This is very simple, that is until ponding T is equal to Tp, what we are assuming, infiltration rate F is equal to I. So, just substitution, and depth of water infiltrated at ponding can be calculated by Fp is equal to I Tp. I is there with us, Tp is there with us, just have to substitute and calculate the value. It is calculated as 0.1 centimeters. The cumulative infiltration at time T is equal to Tp can be calculated by taking the product of rainfall intensity and Tp. So, that is 0.1 centimeters. Next is we need to calculate the infiltration rate. So, at time T is less than or equal to Tp, what is infiltration rate? Infiltration rate F is equal to intensity of rainfall. So, for T is less than or equal to Tp, F can be taken as intensity of rainfall. So, F is nothing but 4.5 centimeters per hour. Now, we can move on to the third part, that is we need to calculate the, we need to first check whether the time given is less than or more than ponding time. Time given is 1 hour and ponding time is 0.2 hours. So, we can understand that the infiltration after ponding needs to be calculated. So, cumulative infiltration at 1 hour of rainfall after ponding needs to be calculated. So, we have been given the values psi and k given, f of p we have calculated, and time t is 1 hour, Tp is 0.02 hour. So, we can understand that T is greater than Tp. So, we need to calculate the infiltration which is occurred after 0.02 hours after ponding time. We will be making use of the equation derived in the previous lecture corresponding to the quantification of infiltrated water after ponding. So, that is given by this equation, and here what we are going to do, we are going to substitute different values given or calculated by us. Delta theta we have calculated to be 0.296, psi delta theta is calculated as 8.65 centimeters, and those values will be substituting here. F minus Fp, Fp for cumulative infiltration at ponding is calculated as 0.1 centimeter, and psi delta theta is 8.65, that we have substituted over here. Ln psi delta theta plus F, 8.65 plus F divided by psi delta theta plus Fp, that is 8.65 plus 0.1 is equal to k T minus Tp. K is 0.05, T is 1 hour, Tp is 0.02 hours. So, this can be, some of the values can be calculated over here, and we can simplify the equation. It will be coming out to be F is equal to 8.65 ln 8.65 plus F divided by 8.75 plus 0.149. Now we are having F on both the sides of the equation. Left hand side also we are having and right hand side also. So, this is the equation similar to that which we have seen in the previous case. We can solve in the same way. We have made use of successive substitution approach. In the similar way, we will be solving this problem also. So, F is given as the same equation I have repeated over here. The method of successive substitution is used to calculate cumulative infiltration at time t is equal to 1 hour. So, first we need to make an assumption for F which is present on the right hand side of the equation. So, that how we have made the assumption? We have taken the trial value as kT, that is k multiplied by t is 1 hour. So, it will be equal to k only, it is 0.05 centimeters. So, this we will be substituting in this equation and we can calculate F as 0.1 centimeter. So, now we will substitute this, we will take this 0.1 as the next assumption and that we will substitute on the right hand side. So, we have substituted, initial guess was 0.05, that has been substituted on the right hand side. We got left hand side, it is rounded off value 0.998 or something it was coming, it is rounded off value and then that is considered as the next assumption and we got the f dash value on the left hand side as 0.15. This again substituted on the right hand side and corresponding value is calculated. This procedure is continued until we get a match between the left hand side f dash and capital F which is assumed on the, which is calculated on the right hand side. Finally, we have found that we are getting exact match at a value of 0.96. 0.96 is substituted on the right hand side, we could get left hand side f of t as 0.96. So, there we can stop when we get the exact match between both the values. So, we can write as after several iterations f converges to 0.96 centimeters. Now, we need to calculate infiltration rate after 1 hour. Cumulative infiltration is calculated after the ponding time. Now, we need to calculate the infiltration rate. Infiltration rate equation is very much familiar to us. So, this is the equation. Here for capital F, we can substitute from the previous calculation. That is 0.05 multiplied by 1 plus 8.65 divided by 0.96. So, it will be coming out to be 0.5 centimeters per hour. Infiltration rate after 1 hour is 0.5 centimeters per hour. As time elapses, rate of infiltration will be decreasing. So, similar kind of examples and also exercise problems can be seen in Ventichow textbook and any other book on engineering hydrology. So, please try to solve maximum number of numerical exercise. Here I am winding up related to the numerical examples related to Green-Ampt equation or infiltration. Thank you very much.